An array transducer is simply a transducer that's been sliced up into a large number of identical narrow strips. Generally, there will be somewhere between 100 and 400 of these strips in a single transducer. Given that the transducer is only a few centimeters in length at most, this means that the strips are obviously very narrow. Every single one of these strips, which we refer to as transducer elements, is separately wired up to the electronics in the probe and therefore can be connected to the machine's electronics. The reason this is useful is because the slicing up of the transducer means that these transducer elements can actually act as independent small transmitters and receivers of ultrasound. In the previous talk, I said this is exactly what we need in order to focus. So the cutting up of the array transducer into a large number of elements like this means that it can be used for electronic focusing of the ultrasound beam. It also enables the scanning of the beam and the steering of the beam, in other words, pointing it in other directions when this is needed. This is a picture of a linear array. So this is a strip of transducer material cut into a large number of identical strips, which, as I said, we call transducer elements. The next idea I'd like to introduce is that only a group of elements is used at any one time to transmit and receive ultrasound. And I've highlighted that in green. So a block of elements, a group of elements, is selected electronically, and only those elements will be used to transmit and receive at one particular time. So the rest of the transducer is not active at that particular time, only that region. So obviously that defines the aperture that the machine will be using, and therefore it defines parameters such as the beam shape. You may be able to see how the machine can scan the beam. This block of transducer elements can be moved. It can be shifted from the left to the right-hand end of the probe, always keeping the same size, so that the aperture can be shifted up and down along the length of the transducer in order to move the beam to different positions. And we'll see later on this is exactly what the machine does. So here we have a side view of the transducer, and you can see it cut up into its elements. I've just as an example said, let us suppose there are 256 elements. That's a binary number. It's not just a number plucked out of the air. And let's suppose 1/2 of the elements, 128, are used at any one time to form the beam. The first beam would be formed using elements 1, 2, 3, 4, up to element number 128. And that would form a focused beam. The machine would transmit down that beam, receive echoes along that beam, and then when it had received all the echoes that were detectable, the beam would be shifted slightly to the right and the process repeated. So here we have the second beam, and it's just simply one element along from the first beam. So it uses elements 2, 3, 4, etc. up to element number 129. It still contains a total of 128 elements, but it's been shifted by just a single element. In other words, it's been moved by just a fraction of a millimeter relative to the first beam. So you can see that there's a large amount of overlap between the beams, and this is one of the features of ultrasound that we'll come back to later. So we saw before that the machine is going to have to transmit at different times from different parts of the transducer in order to get the pulses to arrive at the point of focus at the same time. And this, remember, is to correct for the fact that the pulses have to travel different distances from different parts of the transducer face. So here I'm showing the way the machine achieves this. There's a transmitter package of electronics which creates the actual transmit pulse. This is then connected to each of the elements that is being used via a set of delays. So we have delays, electronic delays, which are interposed between the transmitter and the elements. I've shown just 6 here to keep this diagram relatively simple, but in fact there would be a delay for every single transducer element that was being used. So kind of going back to the previous slide, we would have 128 different delays for that particular case. Notice that the delays vary in their length. You remember that the path distance from the center of the transducer to the point of focus is going to be the shortest distance, and therefore we want that particular element to transmit later than all of the others. And so it correspondingly has the largest delay. So the transmit pulse is delayed by the largest amount before it reaches the central element, because that element is closest to the focal point. If we go to the outside edges of the transducer, you can see that the delay elements are the shortest of any of them, because we want these elements to transmit first, because the path distance from them to the focal point is going to be the longest distance. So the machine calculates the appropriate values for each of these delays and then adjusts them electronically to have the correct values. And this means then it's able to transmit at different times so that the transmit pulses will arrive at that focal point simultaneously, which will give us the highest possible intensity at that one point, and therefore the narrowest beam at that particular point. So that, in a nutshell, is how transmit focusing works. Steering the beam is necessary sometimes. It's required for Doppler ultrasound because the angle between the beam and the direction of blood flow is a critical parameter in Doppler ultrasound. It's also required for some specialized modes of operation, such as compound scanning. So, as I said, steering the beam means pointing it in different directions, and I've shown one particular direction here. Now, at the moment, we're not including focusing in this picture, so this is looking purely at steering the beam. Again, we have the transmitter connected via delays to the transducer, to each of the elements. You'll notice here that the delays vary in length, so that the left-hand element has the longest delay time and therefore it will transmit last. The right-hand element has the shortest delay and therefore it will transmit first. And so when we take that into account, you can see that the machine will send a beam at an angle such as I've shown in this drawing. Again, the machine can calculate the delays necessary to point the beam in any direction that is required. In reality, of course, focusing and steering of the beam are combined, and the delays are calculated to achieve both of those functions in combination. Now there's a little extra variant in the story of focusing. On the left-hand side, we have a machine focusing at a single depth, and I've highlighted it with the white arrow, which you may be able to see. It's focused very superficially, only about 4 millimeters into the tissues. We're looking here at the thyroid gland, so we are looking at a very superficial tissue, and we only have a total depth to this image of around 3 centimeters. On the right-hand side, there are 4 focus markers, which I've highlighted with the 4 arrows. This may seem a bit difficult to understand because it's not possible to focus a beam at the same time at 4 different depths. Instead, the machine achieves this by focusing at first one depth and acquiring the image at that depth, and then focusing at the slightly deeper depth and acquiring the next strip of image information, and so on. So in total, it creates 4 partial images with the focus set accordingly for each of those partial images, and then it combines them together to produce this one final composite image. So whenever you use multiple focus rather than just a single focus, you're actually acquiring the image in strips, as shown here, and this means it's going to take longer to acquire. In fact, it will take 4 times as long to acquire this image because of the 4 focuses. If we have a look on the left, we see that the frame rate is 75 Hz, which means 75 frames per second. A very good high frame rate, which is what we'd expect for such a superficial area. On the right-hand side, where we're using 4 focuses, the frame rate has dropped to 19 Hz, which is approximately 1/4 of the original frame rate of 75. Now, for this particular example, that's probably adequate because it's not a dynamic organ. But if we were scanning deeper, it would probably not be a good idea to use multiple focus because it would slow down the imaging too much. Let's come back now and look at how focusing is done when the machine is receiving ultrasound. So if we think of echoes coming back from a particular depth, then the echoes would be perhaps as I've drawn them here, and you can see once again that they're going to arrive at different points on the face of the transducer at slightly different times because of the different path lengths. Once again, because the point of origin of these echoes is going to be closest to the center of the transducer, that echo will arrive first. So the echo will arrive at the central element first, and it will arrive at the outside edges of the transducer last. Since the echoes are arriving at different elements at different times, the machine again uses delays to compensate for their different arrival times. So the echo in the center arrives first, it's delayed by a longer time. The echoes from the outside arrive last, so they're delayed by a short amount. And these delays are calculated so when we then add together the echoes from all the different elements, they will be in phase. They will add up to give us the maximum possible value, and this therefore guarantees that we're focused at that particular depth. So the machine focuses at a particular depth by calculating the appropriate values for these received delays. You can see this is extremely similar to the transmit focusing. There's one interesting difference, however. You remember that the machine calculates the depth each echo comes from the arrival time of that echo. This means that at any one time, the machine is receiving echoes from just one depth, and the machine knows what that depth is. So the machine is able to calculate the correct received delays, the correct focusing, for the depth at which the echoes are coming from, and to then adjust that moment by moment so that it is always correctly focused while it's receiving. We refer to this as dynamic focusing. So the machine is constantly adjusting and readjusting the receive focusing function to accommodate the fact that the echoes will be coming from progressively greater depths as the microseconds pass. So as time passes, the machine is constantly readjusting the focus, so it's always tracking the depth from which the echoes are coming. So the receive focus is perfect at all depths. The transmit focus is not, because once the transmit pulse has been launched into the tissues, the machine has no further control over it, and so it can only focus at one depth, as I've already discussed. So the transmit focus is at one depth, and that's what the user adjusts on the screen. The receive focus is automatically dynamically swept so that it is always optimum. Now we have a somewhat different transducer. This has been sliced across the width, but also along the length, and so there's now a very large number of elements. Now these transducers are referred to as matrix array transducers, and these do exist. They are commercially available. They're still relatively expensive at this time, but presumably once manufacturing issues have been sorted out, they will become much more widely used and perhaps will eventually become the standard kind of transducer. So a matrix array transducer is likely to have thousands and possibly tens of thousands of elements. And every single one of these elements is connected to the electronics. So you can see there's a great deal of complexity, a step up in complexity from standard probes to matrix array probes. What's the justification for this extra complexity? The answer is now you're able to use electronic focusing across the width of the transducer as well as along the length of the transducer. And this means that the beam can be focused in both of those dimensions, both within the scan plane and across the thickness dimension of the scan plane, which is often called the slice thickness dimension or the elevation plane. We'll come back to that in the next lecture. So matrix array transducers focus better because they can use electronic focusing across the width. That can be adjusted in depth. It can be dynamic when the machine is receiving, etc. So it has all the same advantages. In summary, I've discussed array transducers. I've defined what they are, and I've shown the way the aperture is defined with a linear array by taking a group of elements and using just that group to transmit and receive ultrasound. Incidentally, a curve probe operates in exactly the same way. The only difference is that the curve probe is actually physically curved, and therefore the beam sweeps through the tissues in a different fashion. I've just discussed the way when the machine is transmitting, it can use delays to create a focused beam. It can also use those same delays to steer the beam in different directions. I then discussed the fact that an extension of this idea is the use of multiple focuses, which can be useful in some situations, particularly when you're scanning quite superficially, to improve the uniformity of the focusing. The cost of this, though, is that the frame rate of the image is reduced because the image is actually formed of multiple strips, each with a different focus. I talked about receive focusing, which is very similar to transmit focusing. The received echoes from the elements are delayed and then combined together in a way that focuses at a specific depth. Receive focusing, though, can be dynamic because at any one moment the machine is receiving echoes from a known depth, and therefore it can adjust the delay elements continually so that it is always optimally focused while it's receiving. And then I showed you the matrix array transducer, which is cut up into elements along its length and across its width.